Yuhan Liu.
Yeah, hi, thanks very much for staying until the end. So I will talk about the adversarially robust quantum state learning and testing. This is when I work with Miriam Agarpar-Bova and Naihui Jia. It's recently accepted by FOSS. And obviously it's a quantum talk, as you can see in the title, but I hope my goal of the talk is to convince everyone at the end that it's also not a quantum paper. Okay, so let's see how things go. So I'll start with introducing the necessary quantum background with zero physics knowledge required. And then I will talk about the specific setup and overview of my results. And in the last section, I will go over the technical aspects about it. Many of the ideas are actually heavily related to classical algorithms and statistics. So obviously, you've probably seen it in media and everywhere. So quantum computers have gained significant attention, mainly because it's exponentially faster for a lot of problems compared to the best existing classical algorithm. So one very important example is cracking the RSA. You can do it in time. Quantum computers, but the best known is exponential. So the main advantage of quantum computers is that we replaced classical bits, which is either 0 or 1, into qubits. So qubits, they now enjoy some properties of quantum mechanics. So one of them is superposition. You probably heard about the Schrodinger's cat example. So a qubit can be 0 and 1 at the same time, roughly speaking, until you actually measure it. And then it gives you a deterministic outcome. Another powerful advantage is entanglement, which very roughly speaking, you can make multiple qubits correlated in a very weird way that cannot be described by classical physics. So I'm showing one example here. So here I have two entangled qubits. You can prepare them such that they always produce the same results, equal 0 or both 1 when you measure them. But there's much more to entanglement than this example. Of course, there's no free lunch. So when you enjoy the benefit of quantum mechanics, there's also a curse that also applies. And the difficulty is that since the states are now governed by quantum mechanics, you can also not directly know the states. It's not like classical computers, you can easily read out each bit. So for qubits, you must use measurements to know, to learn what information is stored. But quantum mechanics also says that once you measure, the state would collapse, it will become a different state most of the time. And what you get is only a random classical outcome, only contains some partial information. But in practice, we absolutely need to know what our quantum computer is doing. Like, just think about the last time we debugged a program. Maybe for me, it's like 5 years ago, maybe. So imagine if you write it on a quantum computer, you also need to do the same thing. So, but how are you going to do it when quantum mechanics seems to forbid you to do this? The answer is very simple. Since one copy of the state is not enough, it generates more of them. And one simple strategy is you design some measurement for each of the copies. They can be the same or they can be different. You gather all the outcomes, and then you run some classical algorithms that process the outcomes. Now you probably have a better idea about what the state is, right? So already in this setting, you can see that it looks much like in the classical world, when you want to learn about some properties of the distribution from finite samples, right? So of course, there are more advanced measurement methods, but this simple method is what is compatible with current physics devices, is what people use frequently right now. So we'll focus on this setting. Okay, we solved one problem, but there's another challenge. This is noise, because basically the superposition entanglement is very difficult to maintain physically. So basically, anything can go wrong in short. So your program might be supposed to generate a state, but right now the physical devices are not very good, so they may end up with a totally different state. So that's state preparation. And even if the states are perfect, your measurement process is also a quantum process, so it can also go wrong. So you may not get the desired outcome to hope for. So together, people have a very nice acronym. It's SPAM, so it's just like spam emails. So I think, of course, people know this for a long time, so they devote a lot of efforts. But I want to say the difficulty here is that it's often unrealistic to make assumptions of about what those things are, because those errors can occur unexpectedly, and they can actually depend on your measurements. And of course, even if we set aside the physical factors, there's also an issue of potentially, some malicious attackers that may hack into your computer and do some bad things, right? So basically, what we want to understand is, like, in the very worst case, is it possible to robustly know what our quantum computer is doing? So this is the main problem. So now I'll introduce the specific setup or math. So first of all, so if we have n qubits, then the dimensionality of that quantum state is 2 to the n. So d is 2 to the n exponential the number of qubits. So in general, a quantum state can be expressed by a d by d permission matrix. It's positive semi-definite, and the trace is 1. You should not be scared about this definition. So this shows an example because it's just a mathematical generalization of discrete distributions. So if a quantum state only has diagonal entries, then it's exact discrete distribution over the elements. That's another connection to the classical world. And also, we also need to define some distance notation between states. So for any matrix, you can find the Schatten P norm, which is basically the LP norm of the spectrum. And there are some specific special cases that we care about. So one is the trace norm, is Schatten 1 norm. So the good thing is that when you put the difference between two states inside, it basically generalizes the L1 distance between the discrete distributions. And another special case is Schatten 2 norm, which is also called Frobenius norm. And also I want to familiarize everyone here with the Dirac notation. So you've probably seen this before. This arrow. This means nothing more than just a complex vector. You see the arrow pointing to the other direction. It's just the conjugate principle. It's just a row vector. So now I'll introduce the problem of quantum state learning and testing. So we have an error metric, which is the trace distance. You can think of it as L1 for now. So quantum state learning, or in the physics people also call it as tomography. The goal is to simply learn a full state description with epsilon error. So this, maybe the true state is rho, and you want to obtain an estimated rho hat that's close to it. And there's another problem testing. So you might want your algorithm to generate a state sigma, but you don't know whether it is. So you want to test whether it is generating the desired state or it's epsilon following that state. So if you replace all the quantum states by discrete distributions, they will exactly define. Yes.
So how do you take this trace matrix that's not positive semi-definite?
It's a trace norm. It's the LP norm of the spectrum. You don't take the trace.
The
spectrum of the difference. It can be if
which kind of complex.
Yeah. And yeah, they're all permission. So the spectrum are all real numbers. Yeah, so basically if you replace quantum states by discrete distributions, they just define the problem of distribution learning. Any other problem? Okay. So now I'll introduce the notion of noise here. So we consider the case when gamma fraction of the outcomes are adversarially robust by an adaptive adversary. So basically, the adversary can prepare a state, and your algorithm applies some measurements. The adversary knows sees your measurement, what measurement you are applying, and also the measurement outcomes, and then decide a gamma fraction of outcomes that he can arbitrarily corrupt. And then the adversary sends the corrupted outcomes to your processing. So this shares a lot of similarity with robust statistics. So the question is, okay, if we have sufficiently many copies, can we reliably learn or test the unknown state in this setting? So I want to compare with the weaker noise model people have considered before. We can roughly call it bounded span noise, which roughly speaking, the noise shifts the original outcome distribution by a total variation distance or L1 distance of at most gamma. And we allow the noise to be dependent on the measurement. However, due to a relation between total variation distance and coupling, the gamma correction model can actually simulate this noise model by applying some coupling between the distributions. So, and also in this noise model, there's actually a tomography algorithm that can achieve the optimal error of gamma with sufficient number of copies. So we have a strong model here, but like how exactly quantum algorithms form under the strong model. So we start with the lower bound. It's a testing lower bound. So we say that we can actually, the result is that there exists a state such that no algorithms can test whether a known state is sigma or epsilon far from it. And that epsilon is surprisingly gamma times square root d. So this is very bad news. First of all, because recall that it's similar to L1 distance between distributions. The trace distance is at most a constant. And remember, d is exponential in the number of qubits. So this means that corrupting an exponentially small fraction would ruin any learning algorithm. So this is very exciting result. It seems that we totally uprooted quantum computing, right? So, and also it shows this noise model is much stronger than the previous standard model that people considered. So are we actually doomed, or is quantum computing dead?
Either a classical algorithm is good.
Yes, there is. So
What's the quantitative detail?
Huh?
What's the quantitative detail?
So I guess the most similar setting to the classical case would be if you have samples distributed across different devices, and each device can we send limited information to the server. Yeah, that's a good question. So yeah. So we're not quite doomed because I left some important detail. The state that achieves the lower bound is what people often call pure noise. So in some cases they're useful, but for example, if you want to crack the RSA, you don't want pure noise, algorithm, right? So the useful states are usually have some structure. So one such structure might be the rank of this density matrix. So let's say the rank is R. The previous lower bound would be like gamma times square root R by just looking at an R dimension subspace. So we have an algorithm such that it's actually a tomography algorithm, so we can actually learn the full state description. That's nearly matches this lower up to log factors. And this is the good news, because in many quantum algorithms, rank 1 states are very frequently used. So if you plug in R equals 1, and also the lower bound of gamma would hold for an even weaker noise model than the previous model I described. And also it also holds for the strongest possible type of measurement that I also have not described.
So rank is kind of brittle, what about like stable rank?
Right, but like if you look at any like something, let's say the short sum, they require you to use rank 1 states. So that's a good question. So we might have I guess a more general result would be considered more advanced structures, we'll say, but that's our starting point for now. But I think I guess in the quantum computing communities, they also care about the performance with respect to the brain. Yes.
Is it true that, you know, if you have a matrix of, if you have a state that's very close to rank one state, that you can like approximate that with noise or something?
Approximate that with your noise.
Like as like some noise on your measurement.
I don't know. So the thing is, like, if the rank is low, it's actually very far from pure noise. So it means that you actually can take advantage of those entanglement that.
Sorry, I don't mean the pure noise. I mean like if you have a state that's like very close to rank one state.
Yeah.
How likely is it that a measurement would be different between states? Is it always very unlikely or? There's
It depends on your measurement. Yeah. So, and I think this the most important message is that if you have structural information about your states, then you can help you to fight against the adversary. So now I'll talk about the ideas in the lower bound. So it may be a surprise to if you compare it to some classical robust statistics, because even if we estimate the mean in higher dimensions, you can achieve a dimension independent result. For example, for Gaussians, you can achieve roughly gamma. So why is it not possible here in our setting? The answer lies in the measurements. Because I already kind of mentioned before, each measurement of y only tells some very limited information about the state. So this means that if you want to accurately learn about the state, your algorithm has to be sensitive to small changes in the outcomes. And in most of the cases, having a large sensitivity in algorithm, your algorithm will be less robust. That's the high level idea. So how to actually prove it? So we design a set of states that's epsilon far from our target state. So for the target state, we generate enthalpies, and for the other set, we randomly sample a state for the set. So let's say we have a testing algorithm. So because if there are epsilon separators, the algorithm has to distinguish between the two cases, right? This means that the outcome distributions of the two cases has to be sufficiently separate, and this also considers the randomness when we sample from that epsilon separated set. So what the adversary can do is it can change some fraction of the outcomes to make it look indistinguishable to the other case. And what we show is that the adversary only needs to change roughly epsilon over square root of the effect. But this means that the corruption level cannot be larger than that. So this would naturally imply the lower limit on the other of gamma square root of d. Okay, now I'll talk about the algorithm. So the algorithm heavily uses ideas from robust statistics. So let me start with the standard measurement that people use for tomography. So this measurement, when you apply it, it gives you an outcome, which is a complex unit vector. It's on the unit sphere. And it has nice properties. First of all, it's mean zero. And also you can say the covariance, the complex covariance of that is directly related to the unknown space, as a linear function. So we have a very clear idea. So we just need to robustly estimate that covariance, right? And which is also a mean estimation problem. If we treat that projection vector matrix as a vector, right? So what's the idea to estimate the mean? So we have a bunch of samples. Some of them are good, some of them are corrupting, right? Ideally, we want to exclude all the bad samples and only keep the good ones. Include the empirical mean for that, but that's not possible. Some bad samples could be far, but some could be actually close to the samples. We need to have a way to single out each of them separately. So we take a step back. We try to find a set of good samples. So for example, in this example, like this set of samples may be pretty good. It contains one bad sample, but it's pretty close to most of the other good samples. Right? So how should we do it? So we need to define a criteria or certificates for what do we mean by good subsets. Usually this criteria is defined based on some properties of your underlying distribution. And this criteria should also satisfy that if a subset satisfy this criteria, then the empirical mean over the subset will be close to the true mean. So if we design this criteria that satisfy both, computationally a very simple but inefficient way is to just run a brute force search over all subsets. So we may start with this subset. It's obviously not very good. Maybe next time we look at this, it's also not very good. The next time we end up with this may satisfy our criteria. You're okay with it. Or maybe there is randomness, right? We may also end up with another subset, but this is also good. So how does that criteria look like? So we have an example. If we have a distribution with bounded covariance, the criteria is actually very simple. You just need to find a set that also has bounded empirical covariance, and then you will guarantee with high probability the empirical mean over the set will be gamma square root gamma equals to the mean. And also you can show that with high probability, the gamma corrupted sample also contains such a subset, so we can actually run a brute force search and find the good set. And we don't have to worry too much about computation issues because there are ways to make this combinatorial problems efficient. For example, we can use some filtering method or sum of squares. So we can, of course, apply it to the demography of it.
Sum of squares is really all. Huh? What is the running time?
I think sum of squares for this specific bounded covariance is polynomial in the number sample and dimension, and like already. So, yeah, for this distribution, it's called the question. So if we apply it to the tomography algorithm, so remember we basically want to estimate some mean of this projection matrix. And we can actually bound this covariance if we treat it as a d-squared dimensional vector. It has bounded covariance. The algorithm would output the vector, a d-squared dimensional vector. We can rearrange it into a matrix. And the matrix would have a Frobenius norm of square root gamma to the unknown state. And you can relate this to the trace norm by calculation. And if you want to get a dependence on the ring, you just need to do a projection. Ring power state. Find the closest ring power states that approximates the height. So it's slightly suboptimal, but it conveys the idea of the algorithm. So
but that's the whole place you're using the root d is the coefficient.
Yeah, in the worst case it's square root d, but if there's no say it's ring power.
But any other assumption that makes the coefficient better would also work.
Yes, exactly. Yeah. Yes. Yeah, ring power is one. Low ring is one.
So these stable ring things that you just have like are one very large singular value and other small singular values.
Yeah.
And then the coefficient would be much better.
Yes. Yeah. So I think about those ideas might easily find. So of course it's still slightly suboptimal. The main reason is that the Frobenius norm has a square root gamma, so we want to prove it again. So the idea is that our outcome distribution is actually very well structured. It's only in the sphere. But the previous algorithm only takes advantage of the second one, but it actually has much better bounded higher limits, right? So as an example, for Gaussian distribution, so let's say we have instead the distribution is a Gaussian distribution with roughly the same coefficients. You can actually achieve this roughly gamma error. So, but of course, this distribution is different, so we need a different certificate than Gaussian distributions. So this is one of our main technical contributions. We design a certificate that defines what a good set of outcomes are for this for tomography. So it's called hypercontractility. It's also inspired by some previous work about statistics. So roughly it says that the degree 2 polynomials of the outcome would have bounded higher moments. So, and we don't need like all higher moments. We just need the order to be roughly about 1 over gamma. And moreover, we can kind of like write this criteria as a sum of squares polynomial. So then we can basically apply the sum of squares algorithm to help us like approximately find the subsets, and the subset would create an estimate of the covariance that gives the desired gamma error. And good question, you bring up the sample complexity. If you apply sum of squares here, you have pseudo polynomial sample complexity. So this concludes all the technical parts. So I will also discuss some future directions. So one is obviously to improve that complexity to polynomial in D and monogamy, and ideally to the best sample complexity that can be achieved if you want to achieve an error of gamma. And another like more interesting direction is to apply this idea of adversarial robustness to stronger measurement settings. So one setting would be considered like this adaptive measurement. So you measure all the copies one by one, and you can decide your next measurement based on the outcomes you obtained from previous measurements as well. So this would share, I guess, a lot of similarity to like streaming, the adversarial robust streaming algorithms. And the strongest measurement I mentioned before is called entangled measurement, where you store all the copies in one large quantum computer and just apply anything that's mathematically allowable. So we needed a much different notion of adversarial, the adversary in this setting, but it will be also a very interesting direction. And also another thing is for more practical space, we want to design a truly efficient algorithm, meaning that the sample complexity and time are actually polynomial in the number of qubits, not the dimension. The dimension is actually exponential. So that's the end. Thank you very much. Yes.
This your lower bound. So I wanted to ask, in the lower bound, is it for independent measurements, or is it does it include adaptive measurements?
That does not include that. That's a good question. So that's why I'm leaving the adaptive one for future direction.
Okay,
We're only considering non-adaptive measurements.
so we don't even have a lower bound for that.
No, but I suspect it also holds. But the algorithm is not adaptive, so you can say that in the we have an upper bound of gamma squared root r for adaptive mechanisms as well. Sure. But we are actually in the lower bound.
And in the so your lower end upper bound, they match to constant, right? Do you know?
Up to log factors.
So do you know anything about the constants of their?
They're not even constant. They have some log factors. So
Oh.
yeah.
Okay, thanks.
Maybe the constants are also not very good. Maybe a few hundred.
Any other questions? Okay, let's thank the speaker again.